Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA presentation. This one from the Cloud Storage Technologies Initiative, and today we're going to be talking about 5G industrial private networks and edge data pipelines. It's January the 27th, as you can see, so welcome. Before we go any further, though, I'd like to point out that the copy of this presentation, the slides, will be available on the attachment button or tab on your screen, and you should be able to pick them up and use them for your own use. I'd also like you to rate us on the way out of this presentation. There's a scale of 1 to 5. You can rate us from 1, which is I'd rather be doing something else, really, honestly, why am I here? All the way up to a 5, which is more, please. We love it. And any comments that you have for us about the content would be greatly appreciated. Thank you for doing that before you leave the presentation today. That would be quite terrific. Thank you. So, without further ado, I'd like to introduce our two speakers today. The first is Mukund Shenoy, who's Director of Industrial Connectivity Strategy of the Industrial IoT Group within the Intel Corporation. Good morning, Mukund.
Hi, Alex. Glad to be here. Thanks.
How are you this morning?
Wonderful.
Good. We're also joined by the Chief Architect at AI and Data Science Practice at HP. That's Glyn Bowden. Hello, Glyn.
Hi, Alex. Good to be here.
Good. And for Glyn and I, it's the afternoon. Since we're doing this internationally, Glyn and I are roughly in the same time zone, I think. Mukund is some 8 hours different. My name is Alex McDonald. I'm an independent consultant. I'm the chair of the Cloud Technologies Initiative. So, what is SNIA? Very quickly, at a glance, we're 180 industry-leading organizations with about 2,500 active contributing members, and 50,000 IT end users and storage pros worldwide are on our mailing list, and you today are part of that group. You can learn more about what SNIA does at snia.org/technical. What do we do, though, the Cloud Storage Technologies Initiative? Well, we have mainly 4 goals that we have. Our goals are to do in an industry-neutral way to educate on users on cloud storage, data services, and orchestration, to support and promote various business models and architectures like Kubernetes and object storage, to understand hyperscaler requirements, incorporate them into standards programs that we have, and to collaborate with other industry associations, of which there are many in the IT sphere. So that's what we do in a nutshell. Anything to do with cloud storage that's related to, peripheral to cloud storage, this is why we're talking today on the new exciting technologies surrounding 5G. So just a quick legal notice. This presentation comes to you courtesy of SNIA. We own the copyright. There are no warranties expressed or implied. Use it at your own risk. And basically, the shorter version of that is, it's ours. If you use it, please acknowledge that you're using it, that it comes from SNIA. And secondly, if anything you use it with breaks into 2 pieces, both those parts are yours. They're not our responsibility. So the agenda today, what are we going to be talking about? Well, we're going to be talking about the current state of the industry, how the industrial edge is being transformed. There's a huge amount of development work and change going on in the industry. We're going to talk a lot about 5G and time-sensitive networking. 5G is the greatest white hope of extreme broadband, low latency communications as we move forward. We're going to talk about convergence of high-performance wireless and AI creating new data-intensive use cases. And we're also going to talk about the right data pipeline to provide persistent, trustworthy storage from edge to cloud. So as you can see, this just isn't about cloud storage. This is about all the supporting technologies that go up to make the infrastructure that we're beginning to use in our daily business lives. So without further ado, I'm going to ask Mukund to take us through an introduction to the industrial edge. Mukund, take it away.
Thanks, Alex. And thank you, everybody, for the audience today. I'm very excited to be here. And what I'd like to do in the next, say, 8 or so slides is to share an incredible transformation that's happening in the industrial verticals. And let me share a little bit of why I'm so passionate and interested in sharing this story with you. I had a the privilege of actually witnessing a lot of these transformational changes that happened in the IT side over the turn of the century. And then in the last 21 years or so, working at Intel, I got to see some of the incredible industrial automation systems that go into our factories, and also see the pain points. And the last 4 years or so, I've been working with many of our Intel's lighthouse customers, and had an opportunity to look at some of their pain points in their factories and their visions. So what I want to share with you is that story, and hopefully leave you with some thoughts about how do we take this opportunity and apply it with the kind of changes that are happening in the storage industry. So we'll have that conversation, which Glenn will dive into. So let me move forward over here. Like history a little bit. So let me give you a little bit of a perspective of what this industrial revolutions mean. It all started right around the end of 18th century or so, when we applied the incredible power of water and steam to many of the industrial tasks. And that kicked off what was called, in retrospect, the first industrial revolution. And the reason it was called a revolution was because of the incredible amount of change that it brought across the globe in terms of how tasks were mechanized. The second revolution then followed around the start of the 20th century. This is when electrical power is applied to these tasks. This is when you see Henry Ford did the division of labor, where specialized assembly lines came in to repetitive tasks. And you saw mass production lines pop up in many different industries across the industrial segments. Around 30 years or so, or rather the start of the 1970s, that's when electronics came in, and the power of electronic systems were applied to industrial tasks. We'll talk a little bit more about this in terms of the maturity of our automation systems today, but programmable logic controllers and IT systems robotics were heavily applied over the last few decades to get incredible efficiencies in the industrial space. And what's exciting is this Industry 4.0. You might have heard this term before. This is a moniker essentially that captures the vision, and we are at the cusp of this change that's coming up. Smart factories. Many of these equipment inside the factories are envisioned to take autonomous decisions and start operating in a lights out mode, if you will. Cyber physical systems drive this change. And some of the technologies that we see that are powering that today is the connectivity, big data analysis, machine learning, and such other technologies that are maturing, that's coming in to enable this next generation of industrial revolution. All in all, this is a wonderful opportunity that we need to step back and see what is the implication on our own industry so we can support this transformation. Let's start taking a peek at the Industry 3.0 current state of the industrial automation. If we were to lift the roof of, let's say, an automotive factory, this is something that you might see typically. And this is across many other verticals as well. And by the way, just taking a step back, when we talk about the industrial vertical, I'm referring to many of the manufacturing as well as utilities and other sub-verticals that are all in there. Manufacturing itself includes discrete manufacturing, where you have discrete widgets that are going across a line, like you see over here, in this case, cars, as well as continuous manufacturing, like, for instance, a chemical plant or a pharmaceutical, oil and gas refineries, and even utilities for that matter. One thing that's common essentially is that these have similar sort of automation levels and similar kind of pain points that is triggering some change as new technologies come in. So here in this factory, you see this is typically heavy capital intensive. You see a lot of robots and mechanical devices, machines, etc. All of these are almost hardwired into a system in a configuration that is specialized to develop and produce a certain model of of a product, in this case, a car. There is a lot of compute along the lines. If you notice, all the way from remote IOs, which is a bunch of sensors and actuators at the low level that feed into the programmable logic controllers. These are devices, again, pretty much hard-coded in the line that enable the work in progress to move along the automated assembly line. They allow different robots to do their own work, as well as coordinate the manufacturing across multiple different robots and machines working with each other. A lot of that logic has to be pre-programmed, thought through in terms of how the line operates. And as you work up the way, you see it gets into more high order compute, all the way up to a data center. All of these essentially are configured into what we call the control systems. And if I were to map this very loosely, at least, you see at the lower level, we've got field IO. As I said, this is your sensors and actuators that move things around. That's controlled by the machine control, which then actually is controlled by your manufacturing execution systems and supervisory control systems. The MES and SCADA systems typically look up and down the line so that you can see what kind of work in progress and what kind of demand signals are there, so you can efficiently operate one production line. And then upwards to your enterprise resource planning, such as your SAP systems, if you will, that look at a broader scope, maybe across the whole factory or multiple factories, to do the supply demand planning. So over a period of time, these systems have evolved. You can imagine these are not seamless in terms of their interfaces over here. They've been supported by multiple different ecosystems and supply chain partners, and there's incredible amount of diversity in terms of the kinds of protocols that are used to talk to each other, etc. So this together becomes, on one hand, has provided a lot of efficiency, but also comes up with its own challenges. Typically, what we see is that if you were to look at a factory and have to replan it, data has to be extracted from each level and has to go all the way up if you want to replan a factory, for instance. And this takes incredible amount of effort in terms of human glue required to do the data extraction, abstraction, analysis, and up and down the chain. And even in setting up the systems, it's a significant effort. Like, for instance, one of our automotive manufacturers have mentioned to us that planning the next model takes about an 8-year planning cycle. So all in all, we see that Industry 3.0 is supported by this pyramid architecture, hierarchical systems. And some of the salient problems here are the data is trapped in many of these devices. We've heard stories where we still have, in this day and age, industrial engineers running on the factory floor with thumb drives to extract data from some machines to be able to do the analysis. And this data is now becoming more and more needed to optimize your factories and get more out of them. The hierarchical controls slow down the efficiency and the speed at which you could respond to supply demand changes. So some of these things are what is stopping us from going to that Industry 4.0 vision. Let's look at a case study of an actual automotive manufacturer that I've had the opportunity to work with. We talked about the complexity increasing in manufacturing. This graph I like particularly because it shows that over a period of time, and especially again, I'm looking at the automotive industry over here, you see that the number of products, the variants of the products are increasing significantly over time. This is over decades. But the overall quantity is not increasing at the same rate. So the net effect is the average quantity per variant has been decreasing over time. So this leads to a phenomenon where you have a low volume of a particular model and a high mix of the product variants in your factory. eventually to a batch size of one, right? So in this case, the challenge that manufacturers have is that you have the same product line that you've set up, and now you have all these customizations that are coming in from customer orders. Especially in the automotive industry, we've heard from our customers that the demand is now coming in from individual customers ordering online and choosing specific upgrades or changes to their base model. And so eventually, it becomes a significant logistics problem for them to manage this through the factory. So if you look at some of the implications of this on production systems, you're seeing, this is industry 2.0 when we talked about, it was a single model assembly line, pretty simplistic. The Ford Model T, you have a choice of color as long as it's black, sort of a thing. So you're building to a stock where you've assumed a certain amount of demand, and you put your widgets out on the shelf for public to pick. The current state is more towards the multi-model assembly line. This is where you have a significant amount of downtime on that line, which costs a lot in terms of the capital-intensive machines being down for a long period of time, where people have to go up and do a setup to reset the configuration of the line to crank out a different model of a car. But with all the demand changes that you're seeing, you almost need to go to a batch size of one. What is needed is a mixed model assembly line, where you can see on the last line there, a widget of just batch size of one is essentially needs to be cranked out of the same line, and that produces other lines simultaneously almost. So how are they handling this, right? So there's going back to the principles, right? 8 basic principles of modular assembly, and modular assembly is the key over here, where instead of sending the widgets on a pre-programmed line, what if a car right now is sitting on a mobile robot that can make its way through the factory, and all your equipment is reconfigured to work cells, where each work cell, of course, is doing its specialized operation, but but essentially each of your cars, depending upon what content is needed, can route itself intelligently to the particular work cell it needs to complete the operation, to finish the assembly process. That's a central theme of the modular manufacturing, but there are these different capabilities that evolve that are required to enable this. Reconfigurable work cells, flexible routing of your work in progress, smart line balancing so that you have a good utilization across the line. We need workers to be more connected so you can route them to where their help is needed versus having them fixed in particular assembly jobs with specialized skills. There's also the adaptive production. This is where you don't have to follow a certain path. You can adapt to exactly how the commotion in the factory is. Then you can react to it, if you will. The mobile production over here actually allows you to synchronize your production and logistics. A truck drives in, it's offloaded, and then the parts that are delivered here can be routed to the exact work cell as and when needed, right, just in time, if you will. So a predictive quality control, adaptive control, these are all the tenets of a modular assembly. All of this towards a vision of the factory of the future. And this is what's driving some of the changes that are being expected in how a smart factory, a factory of the future would work. What would you notice here? You can see this concept of batch size of one right away on that assembly line. You have multiple different models, different colors, etc., all running on the same line. And that's possible because your equipment, like your robots over there, for instance, are flexible. You can move them around, you can reconfigure them in a very quick turnaround time. You see these mobile robots that are delivering parts to the particular workstation just in time, like we talked about. The cars themselves are connected, right? There is, the right connectivity elements, like a modem, for instance, now part of the car, and the car can actually, before it becomes even a car, as it goes through the line, at certain point when it's get that connectivity, it can track the changes that's happening, and it can communicate with the factory as to what needs to happen. one of the loaded use cases that we've heard on this is that there are about 83 or so controllers inside of the car, and which needs software download, the firmware that goes into those controllers. And having that remote connectivity, you can delay the download until the last operation of the assembly, so you have the latest version of the firmware in there. And you can even do that as the car rolls off the assembly line and sits in the parking lot, etc. Plus, it's very easy to spot those work in progress and inventory items in the entire factory. Workers are connected. Like I said, we could route workers across to the areas where the particular skills and resources are required. And there are other multiple other use cases that we'll go into a little bit into detail. But in general, you see some of the top use cases are outlined over here, like sensor networks, car to factory, precision quality inspection, mobile robots, etc. And underneath, what we call out here is that the kind of communication requirements that drive this sort of mobile, flexible factory of the future. I mean, wireless connectivity is key. I like this quote from this leading automotive manufacturer that's our customer. It is modularity of the factory. Interconnection becomes the key word, the operational word, to enable that self-organizing production process, right? So this is the exciting change that I wanted to share with you in terms of the motivation that is driving the transformation in automotive. And it's not limited to just automotive. This problem is across multiple different verticals, and we are seeing the same consistent feedback coming from other customers that we have. Alex, can you hear me?
Yes, I can.
For some reason, my mouse doesn't seem to operate with the. Oh, there it is.
No.
I think I'm good. I'm good. It was stuck for a second. I don't know. Can you see my slide move forward? Perfect.
I can. I did.
Awesome. So let's look a little bit about how this underlying automation system, which is a pyramid that we looked at in Industry 3.0, ought to transform. This is the vision of how the automation system actually will evolve, right? So if you look at it, the field level IOs, we see a significant increase in the number of devices, the type of devices, as well as the kinds of communication that these devices need to drive. You see, low latency is a key in doing the controls that are required to power the factory. These sensors also drive significant amount of data volume, for instance, cameras, etc. Right? And the field level IO, you will see that it is actually getting into distributed control units where the PLCs and the IO modules are starting to merge. The PLC function itself, you can think about part of it can be virtualized. What used to be a hardware from a PLC perspective now can be in a virtual PLC. It's a software. And when you see that it's a workload of that nature, you can easily consolidate that to a place where you have better compute options. And you see that workload going up into the local automation cloud. Your MES, SCADA, and the ERP systems that we talked about are also increasingly interacting as well as integrating. So you have more interplay between these systems. So all in all, the field IO data can easily be extracted, worked upon, and fed to the controls, which are placed in the appropriate locations given the latency requirements. And the latency is the key thing, right? The connectivity that between the two blocks, the lower block and the upper block that you see on the right side, becomes significantly important in enabling that transition and transformation. Low latency, as well as very high reliability of communications, because you can imagine many of these functions need safety. Many of these functions need a high reliability in terms of making sure that the operational decisions are made by the devices throughout the factory, etc. And we'll talk about how Wi-Fi, 5G, and other technologies can fit in there. But the overall trend is that there is a disruption of compute, connectivity, as well as storage, as this evolves from 3.0 to support the 4.0 vision. And that's kind of the underlying thing I wanted to bring about in these slides, so we can start parsing through what are those opportunities as things evolve on all of these elements, just compute, connectivity, and storage. I've summarized some of the takeaways here in the IoT devices. Like I mentioned, there is a significant amount of the massive numbers which need one-to-many connectivity, many-to-many connectivity simultaneously, high-performance connectivity, ultra-reliable, high data throughput, low latency, and wireless. And then the on-prem edge. This is something that we will look at in the continuous spectrum in a few slides over here, but I want to introduce the concept of the on-prem compute, where within the four walls of the factory, you have something that where you can run deterministic distributed workloads that you can then orchestrate between the two ends, if you will. Okay. Let's next move on to see what are the enabling technologies that are delivering this. So far we looked at what is the motivation to change, what is the vision to change, and how will things evolve from an automation capabilities perspective. But all this can be envisioned and possible because of some significant capabilities and technologies that are maturing almost simultaneously and interplaying with each other. On one hand, we have these high performance networks, including 5G, as well as Wi-Fi that is evolving in its own way. You've got AI and machine learning, which has been around now and is evolving from a centralized model to a more federated or a distributed model as we look at the various elements of the edges. IoT devices are becoming more sophisticated and being able to provide that flexibility and efficiency required for smart factories. A whole bunch of different devices with a lot of capabilities are evolving. And then the definition of edge itself is being flushed out. We've got the edge to cloud continuum and new models by which the network itself and the compute are merging over here to come up with a distributed network that itself becomes the computer. Let's explore each of these a little bit in terms of how the standards and the current state of maturity of these technologies help in building this future. We talked about the convergence of compute and comms in the earlier slides, but that becomes more important to support this concept of distributed intelligence. On the left-hand side, you see, in the last decade, 4G was very prevalent, Wi-Fi, etc. And then, consumer cell phones and other devices actually were driving that evolution, if you will. AI itself was pretty centralized, and the connectivity is provided by these cellular technologies. But we're seeing a shift towards more of that distributed intelligence model. We talked about the rationale and the motivation for that. We need to have distributed intelligence, distributed decision-making, especially when it comes to the industrial verticals, given the kinds of demands it has in terms of latency and the many-to-many connectivity. So technologies such as 5G and Wi-Fi are evolving to provide that extreme throughput, low latency, reliability capabilities, which enable then the distribution of that intelligence. And we'll talk a little bit about that and the implications on storage in the following slides. But the net of this is that the networks are fundamentally altering the design of how you approach this and becoming distributed computers themselves. Let's look at the definition of edge as it's evolving here. And there's a whole continuum from the IoT to the cloud. I'd like to introduce this this continuum here. On the right-hand side are typically your cloud data centers, the hyperscaler clouds typically sit on that side. And you got the MNOs with the networks today that provide the elements of far edge and near edge. But what's evolving more, especially when we talk about the industrial vertical, is the compute that needs to happen on-prem and the compute that happens on the device itself. And this is driven through the latency requirements of the applications, et cetera, as well as the limitations of the distance that come into picture as you look at the entire spectrum. What I showed there is what we define as the 5G private network, where you have a standalone network given spectrum that is more and more allocated across by governments and policy bodies, if you will, making it easy for private network operators, including enterprises themselves, to apply for this license spectrum and run their own private networks. And in that context, some of the transitions of application towards more distributed architecture can be enabled, if you will. So net effect of this is now you got the ingredient underlying technologies, both from an edge perspective as well as the networking robustness, to start looking at how compute, storage, and analytics now can be distributed across the entire spectrum, if you will. Let's take a quick look at some of the use cases. I won't go into details. We've talked about this to some extent, but here are the top ones that are evolving that need mobility. You got AGVs and AMRs. This is the automated guided vehicles that can move your work in progress and material around in the factory. It's becoming a very important use case to drive efficiencies to support the smart factories of the future. These could be indoor as well as in outdoor factories and warehouses. So you can imagine an AMR that would autonomously actually navigate its way from a warehouse, pick up the goods, move across the campus, get into the indoor factory, and go to the particular workstation and deliver the work by itself, while coordinating with other AMRs running in a swarm or a fleet, if you will. And so if you look at some of the implications, you absolutely need to have mobility, wirelessness, seamless handover, as well as the extreme reliability of navigating through all those territories, if you will, to reliably deliver its stock at the right spot. The compute itself also evolves. You can reimagine, in the past we had AGVs, automated guided vehicles that had to navigate with the help of beacons or strips that were painted on the floor. That's changing now with autonomous robots coming in. You got native 5G precise locationing that will be enabled, as well as, of course, some of the functions will stay on the AGV, but many of the compute workloads can now move to a centralized compute on-premise that can control the entire swarm of AGVs orchestrating the entire factory floor, if you will. And then that's not all of it. You also have the integration required with the ERP, warehouse, and the fleet management systems, which will still continue to stay in the cloud. So here you see one use case where it is spanning the entire spectrum that we saw. It is applying the high performance compute and the connectivity models that are coming in. And obviously the storage implications of this will also evolve and change, if you will. And this is just an example, but all the other use cases that we have, and we have a dozen or so of high value use cases that we have ROI justified. Vision quality inspection is one of them, where we're looking at predictive quality inspection. You take that unlocked data, the product data and the process data coming from equipment. You can essentially build your predictive machine learning models and apply it, so that you could actually send control signals after you have a prediction of the potential quality, and then perhaps even salvage the piece or appropriately tag it for rework, etc. That's bringing in a significant amount of efficiencies and cost savings. Plus, you get a good prediction of your total cost of quality across the line, if you will, if you apply this throughout your manufacturing line. Augmented reality becomes something that will support your connected worker for remote equipment maintenance, facility maintenance, etc. And then the wireless sensor is also evolving as a significant use case that can provide the eyes and ears and other sensing required to run your remote operations from a central on-prem center, if you will. So these are some of the leading use cases, and what I've called out is the evolution of how these applications, and these are your forklifts, things like your forklifts, etc., of the past, evolving to AGVs and AMRs. these applications are being reimagined from the monolithic view of the past to ways by which you can connect it using some of the new technologies, and that's the opportunity we should parse through and see how we can leverage those. One last slide I have here before I turn it over to Glenn is to tell you a little bit about how the 5G transformational capabilities are evolving. I mean, 5G is the 5th generation of cellular technology that has been delivered by the standards body, 3GPP. That's your 3rd generation partnership project. And they've been almost on a decade by decade basis been delivering 3G, 4G, and 5G. Most of us are very familiar with that because of the cell phones, etc. But 5G here is widely considered as being designed for the verticals. Cellular consumers will gain benefits from 5G. Many of us already have 5G phones, but the real capabilities and the standards are being targeted towards how industrial and other verticals can adopt it and transform their operations. These are coming in multiple releases. Release 15 already released in end of 2018, Q4 of 18, was focused around the high capacity data rates. And some of this we already see in our cell phones, if you will. One salient thing that note over here is that the deployments have a lag, as usual, from where the standards are. And this is a very good cadence that has been established over the years. Release 16, which was also, the standards have been fixed in 2020, that focused around the ultra reliable, low latency. So that's your urLLC capabilities, which takes you to about 1 millisecond latency, if you will. So you'll see some of that being applied to non-public networks, which is essentially standalone private networks, if you will. And we expect that the ecosystem will start delivering products in the 22-23 timeframe. That's where the industry is gearing for that. Release 17 is focused more around the mMTC, which is your many-to-many machine type communications, and other things like positioning, etc. And then beyond. Release 18 will pick it from there until eventually you'll roll it over into the 6G space, if you will, where very advanced work for 6G is already started. So this is the salient point here is it used to be cell phone companies and telco equipment manufacturers that used to participate in this 3GPP until the 4G. Now we're looking at more of the industries, and we're seeing active participation by many different vertical industries in providing requirements, providing expectations to the 3GPP so that the standards will be evolved to be adopted by the industry, if you will. So that's kind of the exciting transformation that 5G is bringing. At this point, I'll hand it over back, Alex. I'll hand it to Glenn, and we can look at the implications of some of these changes and technologies on storage. Glenn?
Thank you, Mukund. That's very good. I've actually got a really quick question for you.
Sure.
So we can do it quickly. This looks to me like we're moving back prior to a time before what you called Industry 2.0. We're disaggregating the elements of production completely into small pieces. Is that a fair comment? Have we lost the production line mentality or capability?
That's right. You're right. The Industry 2.0 brought in heavy amount of specialization, etc. And now what we're looking at reimagining those assembly lines that served us for the last 50, 60 years or so, or more even, in trying to figure out how to actually do more modular manufacturing. And to that extent, it is actually uncoupling some of those linked lines. So the concept of the takt time, that the cycle time for one operation, it reminds me of that movie City Lights. With Charlie Chaplin actually showed how we're succumbing to that sort of operation time and get sucked into the machine, right? So I think that we're moving away from that and actually reimagining many of how the lines of the future will be. And so, yeah, you're right. You actually put your finger on that.
Thank you. That's excellent. Good. Thank you. That was a really good overview. So Glyn is going to take us through the implications to enterprise storage, and he's got some big words underneath it: persistent, trustworthy, and secure. Glyn, over to you.
Yeah, I rarely use big words, so I note your surprise there. Thanks, Mukund, for a really awesome sort of overview of what's happening to our industry and our plants. And I'm using awesome in the intention for what the word actually means, right? It really is awe-inspiring. If we look at the amount of change that's happening over such a short period, we really are going to have to run to catch up from all aspects of technology that's supporting that kind of change. So what I want to focus on a little bit now is, what does this mean to storage? And I say enterprise storage here, but actually we're moving way beyond enterprise. We're moving out to the edge, and we'll see sort of how that migration is happening now. So before I do that, edge data is really the next level of transformation. So the thing that's enabling us to do all of this intelligence at the edge is the streams of data that are occurring out there. You can see from this, and this is about all devices, but there's going to be, by 2022, and we're there now, there's 55 billion devices connected worldwide. So that's not an M, that's a B, 55 billion. Now you consider there's only around 8 billion people now. So that's a lot of devices. We're looking also that 50% of data is going to be created and processed, and the key there is and processed, at the edge, outside of where we typically see storage, outside of our typical data centers. So that's a huge shift, and we can see the kind of impact of that shift, if you like, in this graph. Now, this graph spans 30 years, right, from 2010 up to 2040. Now, the blue line is the growth of data center storage. So the amount of data that we're growing within our traditional core data centers on our traditional platforms. And you can see it's kind of flattening out there, as we're still on a kind of an upward curve at the moment, but we're going to see it start flattening out and even start to dip down as we end up at sort of 2040. The edge, on the other hand, has started from nearly zero in 2010. And by 2025, it's going to be the tipping point. We're now 3 years away from that tipping point. And you can see, but actually, by the time we get up to 2040, we'll see 364 times the amount of storage growth at the edge than we will in the data centers. So we can see what our mission is in terms of storage professionals, where we have to start looking, where we have to start considering how we place our technology and how we think about data and the data movement within our organizations. So I want to take a quick step back. So Mukund talked about some really good and interesting use cases around things like visual inspection. So how do we do it today? Well, we do it today by having somebody look at this stuff, right? So we've got a human being that's looking at bits of taking samples off the production line and actually visually inspecting it and saying, yes, this is good, or no, this is bad. Now, the human eye, a single image is around 5 to 15 megapixels. That's when you're focusing at it. If you look at the actual very center of that image, it's around 576 megapixels. So that's where our absolute focus is. Now it gets blurry and blurry as we go towards the edge. So that's a reasonably sort of high intensity image, and that's from the human eye. Now, if we have a look at sort of where our sensors are coming, where our camera sensors are going, now bear in mind that eye is up there at that 500 megapixel piece. The sensitivity of camera sensors and image sensors that we have in our equipment today is increasing massively and exponentially. And you can see we're already well on the way to being equivalent to the human eye in terms of the amount we can see from the absolute core perspective. And in fact, a lot of the time, because we can have that level of sensitivity across much broader fields, we're capturing much more data than the human eye can. Why is that important? Why is this needed anyway? And the reason being is, if you look at precision engineering, if you're trying to find faults within precision engineering, and faults could be a number of different things. It could be something that's not orientated correctly when it comes out of a machine, something that is discolored when it comes out of the machine, meaning that there's been vibration, or meaning that there's been heat applied to it in some way. All of these very slight changes in terms of the threshold of acceptability, if you like, need to be noticed. So if you're taking images of that, you need extremely high resolutions in order to be sensitive enough to detect those sorts of variants as they're coming off the equipment. So we're building these sensors that are capable of extremely high resolution, extremely sensitive, and across larger and larger color palettes as well, so we can detect heat and color change and those sorts of things. All of this is, of course, data. So as you create all of those new megapixels, so you have more data that you're creating per image. And when you're looking at video streams coming off these things, or many images being captured per second, because very often we have production lines where things are flying through at hundreds, thousands, or even millions of items per second, then you can see that curve of what we need to store goes up very quickly. So what we want to dig into actually is, what are we storing? So let's look at the kind of traditional model. This is a slightly different version of the model that McCunn showed us. Actually, it's exactly the same model. There's just some slightly different words in there, and I've used words instead of pictures. But you can see that we start off in this traditional space. So that's our cloud storage. Now, cloud could be within the data center, but let's assume public cloud for the moment. So we've got a large amount of data that we have in the public cloud. We know how to manage that now. That's fairly sort of easy to us. We also have our traditional storage arrays, if you like, that happen at the network edge. And what I mean by that is, you have the cloud pieces, so that's your public cloud vendors. The internet edge is really the edge services that those public cloud vendors offer, so where we connect into them. So they still own the infrastructure, but it's at the edge of their networks. We then get into our network edge. So that's where our data centers exposed to the world. And that's where our typical traditional storage arrays sit. So where your SAN arrays, where your NAS arrays, all those sorts of things, that's where they live. We know how to manage those things. Very often we're mirroring data between those. So it's a like for like in terms of the data experience, if you like. Now, as we move out, we're looking at sort of within factories, within hospitals, all those sorts of areas. You have what we call the micro data centers, which are basically data closets or server rooms that live in cupboards or live in very small form factors that sit within these buildings. So it could be within a factory. You might have a reasonably sized data center for a lot of sort of small organizations, but actually from an enterprise perspective, it's a micro data center. So you'll have some smaller storage arrays there just to support local applications and local sort of data usage. It may be that it's supporting other systems that don't leave the premise, for example. And what we typically do is we'll back up data from those things back into our central location, and we'll possibly push data out as well to those locations as well, so it can be used by the applications. Now, when you start getting out to that device edge, the way we have to manage storage or the way we interpret storage becomes very different. We're suddenly looking at lots and lots of little instances. Now, they could be on mini devices. It could be a stream of data that never gets persisted. But it's much more around the number of and proliferation of devices rather than it is a single storage device. And you can see that we have to do some data movement back and forth from that device edge into the enterprise edge, and then all the way back into the cloud. And actually, what you often find is those devices will talk directly to cloud storage, so that you're centralizing to an instance that's usually local to that. So that's the sort of model that I think most people expect when they see sort of the edge storage, and this is where most of our minds go. However, there's a couple of new data services or data activities that have to happen at the same time. So firstly, there's the filtering. Do we take everything that we capture back at the edge and from those devices? Does everything have to go back to that micro data center or even to the cloud? And the answer is no. In fact, the bandwidth doesn't exist yet to be able to do that. So, and there may not even be a reason underpinning the ability to do that either. So it doesn't necessarily exist. Again, we now need to put some filtering in between our micro data center and our data centers themselves, our cores. So do we need everything that exists in the micro data center to go back? Again, the answer is probably no. We want to be doing aggregates of that data, output of data modeling, that kind of thing will then go back into the data center. Sampling also goes back into the data center so that we can retrain models and do refinement when we're not already doing that activity at the edge. And then, of course, there's the big arrow. A lot of that stuff is just going to go into the bin. If you're taking 1 million pictures a second of a piece of equipment, you're probably not going to want to capture all of that, because you're going to get an awful lot of pictures of exactly the same thing. So imagine if you go on vacation, you take 1 million pictures of a church. You're not going to want all of 1 million pictures. You pick the 1 or 2 best, everything else goes. Now, the reason why that might not be the case for all data that's happening at the edge is you will need some to go back and do that model refinement and the retraining of AI and ML that you'll necessarily see for the inference pieces that are happening at the edge, where you can't do that training at the edge. Now, what often happens is when you have an anomaly detected through that inference, you will then start streaming both the data that happened maybe 5 to 10 minutes before, or even up to an hour before, and an hour after. What you don't want to do is only send those anomalies back to the core, because what you end up then is a data set full of only anomalies, and it's very difficult to detect what's normal when you only have anomalies. So you do have periods where you'll be streaming data back into the core, but the filters are there to make sure you don't overwhelm the infrastructure that sits southbound to that. So that's our kind of migration storage and how we see sort of the data moving out. Now, what that means is we can really classify where the data sits by these certain terms. So when it's at the edge, it's much more urgent data. It's data we want to act on immediately. Mukund was talking about the very low latency to be able to do that command and control of the infrastructure and the robotics, and even the sort of mobility pieces. So as you have the autonomous vehicles driving around, they really need that high urgency. It's no good having the data for them and their environments going back to the data center, getting lost in some latency and a BGP routing issue so that they go flying into a wall back at the factory. So you need everything processed locally, and they have that high urgency data. Now, a lot of that urgency data doesn't need to be persisted. So it's hot and it's active immediately, but it has very, very little value after the fact. The fact there's a wall in front of the device that's moving around, or the fact that something has happened on the machine line, may be entirely irrelevant once that time has passed. So a lot of it is very time sensitive. As you go back towards the kind of clouds and the data centers, it's much lower urgency stuff. So it's stuff that you'll probably want to be replaying in order to validate things. And it's stuff that you might want to be plugging into something like a digital twin to play through scenarios. It's very sort of easy then to kind of keep that in the archive and replay it over and over again. And again, that's the result of that filter. But it's not something that has to be live, because the live data is really where the decisions are being made. So finally, then, let's look at what one of these data pipelines might start to look like as we move forward. And this is typically what we see deployed with our customers that I've worked with in the factory space. And I'm sure Mukund will have a very similar picture for the folks he works with. And you really have, starting at the left-hand side, it's all around that kind of data acquisition piece. So it's often in a proprietary format. It's often very difficult to kind of get out. It's what we call the IT-OT link. So the IT is the information technology, OT is operational technology, and it's where the two worlds come together. Now, IT folks often struggle with that interface because its protocols are not used to seeing, its formats are not used to seeing, and it sort of complicates the management of those devices, if you like, in the fleet, and also the huge scale that's not being used to seeing. So that comes into our data flow management. We'll typically have things that are attached to that are doing the types of stream analytics we've been talking around. So that could be machine learning models, that could be straightforward analytic pipelines, that could be decision engines, that could be command and control. Ideally, as we look at the kind of modularity that Mukund was talking about that we're evolving to, that pipeline needs to be modular as well and dynamic, so that we can reroute data and we can reroute telemetry and activity as the process evolves, or as we change use cases and scenarios. So we're looking to build sort of modular and dynamic pipelines of data. That kind of leads us into that data lake and data archive. So as we begin to move these things back into the core, or even to our edge data centers, we have that versatile data access. And that means that we need ways of visualizing that data as well. So not just capturing it and having it make decisions for us, but how do we make sure the operators have visibility as to what's going on? We're seeing much more demand around data transparency, so that we can really understand where our data is coming from, what decisions it's been involved in making, and then we can go back and look at why certain decisions have been made. And then as we kind of move through the right, we get the more colder use cases, if you like. So things like the batch analytics, the training of the AI, machine learning and deep learning models, and even high performance compute simulations, which can converge with AI and ML to build digital twins. And that digital twin is really something that we can then use to simulate what's happening on the factory floor and provide what if scenarios and those sorts of things as well. So this is the type of data pipeline we're going to see to start emerging. So finally, in summary, 5G is massively increasing our opportunities and capabilities of what we can do at the edge, particularly sort of in industrial environments. And command and control is now far more remote than ever before. It's happening on the devices themselves and in that mesh of devices as a swarm, or as the fleet, as Mukund was referring to, than just being sort of driven out of that core place. But that sensor and generated data are growing extremely rapidly, far faster than our ability to ship that data back into the storage at our core. So we're now having to have cache layers, we're now having to have data pipelines that exist at the edge all the way down to that device, so that we can do data services such as filtering, such as command and control, such as backup, that are happening within that edge device. Your storage and data strategy absolutely must include the edge and must evolve to be focused on how do we manage storage at the edge. And that's what I wanted to cover. Back to Alex. Thank you.
Thank you, Glenn. And Glenn, you know, scary thought here, because I think you actually said at one point, we know how to manage cloud storage. Goodness, you know, that's a pretty big assumption. It certainly looks like a big issue. In fact, I'm going to ask you both the same question because it fascinates me. The question I'm going to ask you both is about bandwidth. One of the things we've talked about is low latency, but the amount of bandwidth required for some of this stuff is words like you talked about awesome. I'm thinking about frightening. I'll start with you, Glenn. Where do we get this bandwidth from? What does the future look like in terms of bandwidth?
So really, it's where the bandwidth exists is becoming the first conversations. So with the kind of emergence of things like 5G and Wi-Fi 6 and all those bits and pieces, we're increasing the amount of actual network bandwidth available to us. But what we know about that is it becomes very short range. So if you look at 5G, for example, I think or at least in kind of the micro size, I think we have somewhere in the range of 80 feet that we could actually be away from a transmitter of some kind. Now within a premise, that's fine, but we're not going to be able to transmit beyond that. So what we're doing instead is we're taking the capabilities of compute and accelerators that we need and moving them much closer to the actual sensors and where the activity is taking place. That is what's driving this move to the edge, is the requirement not to have that bandwidth stretched between two remote locations or distant locations. So it's not just about how do we make the bandwidth faster, if you like, but it's how do we use it better and how do we shorten the distance that we have to travel with that bandwidth as well, which gives us more lanes and more capabilities and more opportunities there. And that way we can also start to use other things for that bandwidth. So if we're on device, for example, we can start using things like PCI lanes rather than having to go into a network piece in order to be able to get the bandwidth for the type of imagery and things like that we need to move.
Okay, McCann, can you answer the same question? I'm going to modify it slightly. Are we seeing the end of wired networks?
No, absolutely not. Actually, it is about coexistence of wired and wireless technologies. We'll see many of these, even wireless technologies, coexist in the future. Glenn actually hit the nail on the spot in terms of answering the bandwidth question. It's about using bandwidth the right way. I think he gave very good examples of how data will be filtered, etc. And then it's a balance between bandwidth and latency as well. Latency becomes very important here as well, because the control command kind of traffic is probably not high bandwidth, but needs really low latency. So it's matter of optimizing your network to configure it to do several of these things simultaneously. And that's been a challenge in the past. And I think these high performance networks provide that. And once that is in place, the reliability comes in, and the applications can be reimagined so that you can and storage as well. So you can move the storage to the right locations where it's needed to meet the latency. And then also, depending upon how the filtering happens for the sake of applying new machine learning models, etc., you can fine tune the networks to deliver those capabilities. Did that sort of answer the question?
Yeah, it does. Thank you. The other question I've got for you is about, is anybody actually doing this right now, this Industry 4.0 stuff? I mean, are they big investments, or are they small? Are they tentative? Where are we?
That's a great question. Actually, the ball is already beginning to roll on this. It's a multi-year journey. I mean, industrials, I should say, in general, are very conservative, very risk averse. So the transition takes time so that you create a lot of proof points, etc. So many of the standards, as they start evolving and are being accepted, the ecosystem has already been mobilized. Many companies have significantly invested. Like I mentioned, we work with some lighthouse customers who have R&D groups that are focusing on some of this research and development and creating early proof points. And depending upon the use cases, and there are many areas where, like for instance, advanced machine learning and AI models are being applied today in production lines. And as 5G network standards for Release 16 will evolve, you'll see that in the next 3 years, large companies will offer some of private networks standalone for industrial. A lot of that is already happening. Many of the MNOs have also, we already positioned themselves to offer that. So you'll see that within the next 3 years, this will start moving from early prototyping and proof of concepts into large-scale deployments. That's the expectation at this point. Good,
thank you. Listen, I'd like to thank you both very much, both Glenn and McCann, for the excellent presentation. Really interesting stuff. Thanks for viewing this webcast. As I reminded you at the beginning, if you could rate the presentation, provide us with feedback on the way out, that would be terrific. We'll be posting a copy of the slides on the Educational Library. They're already available in the attachment tab. And we'll also do a Q&A from this webcast to try and answer any unanswered questions we didn't get to during the presentation on SNIACLOUD.com. You can also follow us on Twitter if that's your particular interface into the world of social media. In the meanwhile, thank you very much, McCann. Thank you very much, Glenn. And thank you all for attending this presentation. Have a great day. Thank you.
Thank you.